All right, pre-calculus, first day in chapter 5. You're going to be using fundamental identities. We're going to actually be doing some algebra with them and some calculations, and they review some of the formulas that you've had before. You will be given these identity sheets for on your assessments, but so feel free to use them in your homework. But the more that you know them, the easier it will be to know what possibilities you have to simplify expressions. And the first ones, I hope that you already know, reciprocals. Sine starts with an S, its reciprocal starts with a C, it's 1 over cosecant. And it's true the other way, cosecant is 1 over sine. Cosine starts with a C, its reciprocal starts with an S, and if it's secant, you can change it to 1 over cosine. And the reciprocal of tangent is cotangent, and vice versa. Those I feel like people have down pretty well. But then tangent is sine over cosine. And we had that at the beginning, I think, of last chapter, but we kind of didn't use it a lot. But also remember that tangent is defined to be y over x on the unit circle. And on the unit circle, the y value corresponds with sine, and the x value corresponds with cosine. So tangent is y over x is sine over cosine, thinking about it that way. And the reciprocal then, cotangent is your x over y, cosine over sine. By the way, they have u as the argument. You will see things like kind of a scripted b, that's beta. You will see this symbol, which is alpha. You will see theta. You will see t. You might see a v or an x. All of those can be used in the argument spots. Whatever they are using, stick with it and keep the same symbol. All right, but then we have the Pythagorean identity. And when you are working on the unit circle, the unit circle is x squared plus y squared equals 1. A circle centered at the origin with a radius of 1. Well, on the trig, we've talked about cosine, and then sine for our x and our y. And so if I think about it that way, I get cosine of u squared plus sine of u squared equals 1. And just a notation, cosine of u squared is going to be written as cosine squared of u. It means the same thing. It means the same thing. So same thing with sine. Sine of u squared is the same as sine squared u. It means you're taking it times itself twice. And so using that, we get a Pythagorean identity. It's a Pythagorean theorem. And here we have Pythagorean identity. Sine squared plus cosine squared u equals 1. And it is typical that we write that with sine squared first. And so that is something that you will be replacing 1 with sine squared plus cosine squared. Or you will see sine squared, cosine squared, and replace it with 1. You're going to be substituting equals for equals. And then you need to note some rearrangements of this. Sometimes we try to put everything into the same trig function. So we want to put everything, say, into sine squared. Then any cosine squared, we will replace with 1 minus sine squared. That's just subtracting the sine squared over to the right. It's just making use of structure. It's just moving sine squared to the right. So if everything else is in terms of sine, and you have this 1 cosine squared, we can replace cosine squared with 1 minus sine squared. And vice versa. If everything's in terms of cosine and you see a sine squared, I can replace it with 1 minus cosine squared. Caution. You cannot just, this is a no. Some people think that you can just take the square root of this and take the square root of this and make cosine u equal to 1 minus sine u. But this is not true. The square root of a squared minus b squared is not a minus b. You can't, when it's addition and subtraction, you can't take their individual square roots. So you can't just drop the squares and think that you took the square root of both sides and use those for substitutions. All right, now, if I start with sine squared u plus cosine squared u, so that's that Pythagorean theorem, x squared plus y squared equals 1 from the unit circle. And I divide each term by cosine squared. So I'm dividing both sides by cosine squared. You have something that's equal, it's legal to divide both sides by it. Well, sine over cosine is tangent. So if it's sine squared over cosine squared, this is tangent squared. And cosine over cosine is 1. And the reciprocal of cosine starts with a c, its reciprocal starts with an x. And they typically write it with the 1 first. And that's how you can develop that second Pythagorean identity. And then just like we did up above, if things are in terms of secant and you have a tangent squared, you could replace the tangent squared with secant squared u minus 1. It's a rearrangement just of that second Pythagorean identity. Likewise, I could solve it for 1. Maybe for some reason you got into something and you see a secant squared minus tangent squared, you could replace it with 1. All right, and then for the last Pythagorean identity, if I start with the sine squared plus cosine squared equaling 1, and instead of dividing by cosine squared, if I divide by sine squared, then I get a 1. And cosine over sine, it's your x over your y, it's your tangent, or cotangent squared, excuse me. And the reciprocal of sine starts with an s. Its reciprocal is cosecant squared. And that gets you your third Pythagorean identity. And then we can rearrange it. I can solve it for cotangent squared. And I can solve it for 1. So we have these Pythagorean identities and rearrangements of them. I'm not going to give you the rearrangements. You should be able to manipulate that to come up with these two. You should be able to manipulate this one to come up with these two. You should be able to manipulate this one to come up with these two. You just get these three. And then we're not going to worry about the cofunction identities. But we do have some even and odd identities. We want to be able to rewrite these. And now this one's it's hard because we're not developing the whole concept behind it for evens and odds. Because people think that we are taking the negative out in front, and that is not conceptually accurate. Even and odd functions, you had this in another chapter, and for them to be even, f of a negative x comes out to be f of x. And that's true when they are even. But f of a negative x comes out to be the opposite of f of x when the functions are odd. And so you only have two that are even. Its cosine and its reciprocal function. And notice that you don't get a negative function. And part of that is because the cosine graph goes like this, and if you fold it on the y-axis, it has symmetry with the y-axis, it is an even function. That's what an even function is. If I put x, I get the same value as if I put negative x, because I have the same height. That's the concept behind it. Cosine and secant are both even functions. And why do we have these? Because I want to write these with functions with positive angles. I want to get rid of the negative angle here. And so if you're evaluating on the unit circle and you have the cosine of a negative 30 degrees, that's not a problem because you can evaluate it. But when you're simplifying trig functions and you're not evaluating for specific values and you have a negative angle, you don't want that negative angle in there. And so I can replace cosine of a negative u with cosine of a positive u because it is a even function. But then sine and cosecant and tangent and cotangent are odd functions. And so the definition of odd is the f of a negative x comes out the opposite of f of x. For sine, the sine graph looks something like this from negative pi halves to pi halves. If I put a positive x in, I get a positive height, but if I put the negative x in, I get a negative height, the opposite of it. And that's what's happening with the odd functions. So when I see sine of a negative u, it is not that I'm taking the negative out in front. That is not what's happening, because notice if that was the case, then this would come out to a negative cosine u, and it doesn't. It is because of the application of it being an odd function that I can replace this with a negative sign. And then same thing with its reciprocal. Tangent's also odd. The tangent function looks like this. A positive x puts out a positive value, and the opposite of x puts a negative, the opposite of it, out. So anyway, so this is what you use when you need to not have a negative angle in front, when it's a variable like this, and you can replace those. Using identities to evaluate a function. This actually goes back to some processes that you've had before. And one of the first things is figuring out what quadrant are we in. Because they want you to evaluate all 6 trig functions, and when I know what quadrant I'm in, then I know the signs. And you have 2 pieces of information. Oops. The secant is negative. And that means cosine's negative. So there's 2 quadrants where cosine is negative. Cosine's the x. It's quadrant 2 and 3. So when secant's negative, I know it's 2 or it is quadrant 3. And then tangent is positive. Tangent's positive in quadrants 1 and 3. That's a fancy way of saying tangent's positive. So tangent's positive 1 or 3, and they both have to be true, so they both involve quadrant 3, so I know it's in quadrant 3. And that means tangent and cotangent are positive and the other 4 trig functions are negative. And the textbook is going to go back to the trig identity with secant squared and tangent squared, and it doesn't really matter which one we use. And it's going to do this tangent squared u plus 1 is secant squared u. So I'm going to show you 2 methods. Second is that doesn't correspond with how I've taught it before. And this is the Mrs. Remington's way, is that the secant of x is -3. So that means the reciprocal, the cosine, is a -1/3. And cosine is adjacent over hypotenuse. And you are in quadrant 3, so I'm going to draw a triangle in quadrant 3, and this is my reference angle x. And so my adjacent is -1, and my hypotenuse is 3. And then this is my y value, and a squared plus b squared equals c squared. And I get y is plus or minus 8, which I'm going to write. It's -2√2 because it's in quadrant 3 and y is negative there. And from that, I can do all 6 trig functions. Because then we've got secant, so cosine we already have, and use your argument is the reciprocal. So we've got secant, we've got cosine. Sine is the y-coordinate. Well, it's actually, you've got to do opposite over hypotenuse because the hypotenuse is not 1. So it's -2√2 over 3. And that's reciprocal cosecant is -3 over 2√2. And then you need to rationalize that. And tangent is your y over your x. Opposite over adjacent. And cotangent is the reciprocal of that. But you have to rationalize. Oh, over 4. My fault. And so that's how I like to do it. I like to figure out what quadrant, you need to figure out what quadrant you're in regardless of which method you do. And I like to draw the triangle. And that seems consistent with what I've done in the past. But they are using the trig function, so they're going to see that secant's -3. They're going to come up here and find something that involves the secant. And they're going to plug into that to find the tangent. And so they're going to say tangent squared of u plus 1 is the -3 squared. So tangent squared of u is going to be 9 minus 1. So tangent squared of u is 8. And the tangent of u is plus or minus the square root of 8. And you need to pick the positive You need to pick the positive because you have to have figured out that you're in quadrant 3. And so that's the y coordinate there. But you still need to then from there set up a triangle and use the fact that tangent is y over x. And you have to realize that since that you're in quadrant 3, that the x has to be negative. And you have to also figure out using the secant that this is 3. I just like setting up the triangle, but you're going to see work like this. And it's just not how I do it. I do it using a triangle. All right, so next page. I want to caution you strongly to not go right to the worked out answer keys. Don't just have them there and go to it as if you don't train your brain to pick out things to use, it might make sense to see how someone else has worked it out, but you won't have the skills on a test to do it for yourself. It's uber important on this. And so you are going to simplify trig functions using the identities from the front. That's another reason why it's good to have them memorized, because that frees up some RAM in your brain to problem solve, because it's right there. And so there's all kinds of things that we're going to do, starting with just expressions. One of the things you can look for is change everything to sine and cosine for beginning problems. That's not a bad way to go about simplifying. You also want to look for common factors. And you want to identify the different formats of the Pythagorean theorem identities. So there's quite a bit happening there. So simplifying. Here they're using alpha. That's what that's called. And so we're going to continue to use that. I have one trig function in terms of cosine. The other is tangent. Write this down on your paper. Always copy the original. And then drop down to the line below. And it's a good idea here to change to sine and cosine. Tangent's y over x. The y is sine, the x is cosine. So tangent is sine alpha over cosine alpha. And then that is times cosine alpha, and that's considered to be over 1. And when you're multiplying, it's okay to cancel those. Don't forget we call it the argument. Alpha's in the argument spot. If you just write, you will not be getting full credit because you need the angle. This is a don't do it. And then this just becomes sine alpha. And the other thing when you simplify, it's like, how do I know I'm done? By doing enough of them where you get an intuitive sense that you're done, knowing the identities well enough to know that you can't substitute something else in to make it look simpler. All right, in part B. Oh, I could change everything to sine and cosine. But each term, and eventually I will, but each term has a secant. And so I can factor out a secant. And when I do that, what's left inside there is what I get when I divide each term by secant. These cancel, but that's not 0, it's 1. And these cancel, and you have a minus sine squared x. For your sine squared, I'm going to write theta, plus cosine squared theta equaling 1. We very frequently use these alternate arrangements to the point where I hope that you very quickly pick up 1 minus sine squared x is cosine squared. 1 minus sine squared is cosine squared. So this is going to be cosine squared. This right here is cosine squared. And, oh, wait a minute, secant, the reciprocal is 1 over cosine. Knowing that secant's 1 over cosine brings that about a lot faster than if you have to look at all the identities. And the cosine squared is really over 1, and this takes out one of those, and you are just left with cosine x. As you do these, you write down the original, you drop down, not left to right, you start with an equal sign on each line, box your final answer. You have to train yourself to look for common factors because it's a little abstract. It's not something you've seen before with trig functions. So you need to train yourself on that. All right, on the next one, we do not have anything that is squared at this point. So I'm not using Pythagorean identities. And if I'm not using Pythagorean identities, there's no negative angles here. We're talking about reciprocal identities and where tangents, sine over cosine, cotangents, cosine over sine. I would choose to change everything to sine and cosine. You get a mix. So, I'm going to come down here. The major fraction bar should be the longest. And sine, I'm going to think of as just over 1. And secant is 1 over cosine. Something to try. Nothing's being squared. Change everything to sine and cosine. And tangent is sine over cosine. I've seen students make errors because they don't make the major fraction bar long enough, and they get mixed up in terms of what's in the numerator versus the denominator. So organization, clear organization is important. All right, so the numerator is sine theta over cosine theta, and the denominator is sine theta over cosine theta. And so what we are doing here is when you divide, you multiply by the reciprocal. When you divide, you multiply by the reciprocal. And across multiplication, the sines cancel, the cosines cancel. That's not 0, it is 1. Of course, if you recognized up here and said this cancels with this because they're the same and wrote 1, I would accept it. Watch communication. When you cancel things, you have to do it in a way that I can still see what's underneath there, so I can know you did the right algebra. In part D, 1 minus cosine squared brings to mind Pythagorean identity. We have sine squared theta plus cosine squared theta is 1. And if I move the cosine squared over to the right, I see that 1 minus cosine squared. And so 1 minus cosine squared is sine squared. You're going to use that a lot, so hopefully that will become something that you're able to identify right away. So 1 minus cosine squared is sine squared. I do not want to bring in the tangent squared Pythagorean identity, because then the tangent squared identity would bring in the secant squared. The tangent squared would bring in the secant squared. And I would rather just try to go towards changing everything to sine and cosine. And there's not always just one way to do these either. But here, the sine squared, major fraction, and tangent is sine squared over cosine squared. And so then you get your numerator of sine squared times the reciprocal of the denominator. You need to remember that that's a fraction in the denominator, so multiply the numerator by its reciprocal. And the sine squareds over 1, they cancel, and you get cosine squared theta. An alternate route is after you replace the numerator with sine squared, 1 over tangent squared is cotangent squared. So you could say, well, the reciprocal of tangent is cotangent, so I technically have a 1 over tangent. I can make it cotangent in the numerator, and then cotangent is cosine over sine squared. And you get cosine or something that way. And it takes a while to, have some fluency on these and see different things to do. This is, I said, it's abstract, it's different. Do not just copy from the answer key. You will be in trouble when it comes time for the test. You will have questions where we'd ask you to just plain old factor with trig functions. This is, so we're going to start with just flat out factoring. And we're treating this like we would sine squared would be like y squared minus x squared. And a difference of squares factors y plus x, y minus x. If you need to do some work like that off to the side, do it off to the side. I want you to present your answers as copy the original. And this is a difference of squares. And it's factoring. It's different than simplify the expression. We're factoring. And you get a sine x plus cosine x. And a sine x minus cosine x. We're not simplifying, we're just factoring. And that's it. You factored it. Oops, that's not what I want to do at all. All right, so on the next one, see this as, say, 3x squared plus 2x minus 8. Think of it as quadratic. You have a cosecant squared, then a cosecant, and then an 8. To get a 3 cosecant, you're going to have a 3 cosecant x in the first and a cosecant x in the second. So that when you multiply the firsts, you get a 3 cosecant squared x. So it's as though you're doing a 3x here and an x here. And then you need numbers that will multiply to 8, but the outer and inner product add up to 2. So if I try a minus 4, this isn't the right one, and a plus 2. Oh, actually, my brain did it right. I tried to do it wrong. You get a 6x and a minus 4x, and that is 2x. I tried to do it wrong, but my brain just put it in there correctly. And so that's what we're going to have here, a minus 4 and a plus 2. And your check is if the outer product plus the inner product add up to be a positive 2 cosecant x. If you FOIL them back out, do you get what you started with? Yes, question.
I'm sorry, is it okay if you can turn off the fan?
Oh, I'm sorry.
Because it's like right at its cold.
Sorry, I should have turned it this way. I'm so sorry.
No, it's okay. Thank you.
I had the fan going, so they were freezing to death. Sorry. All right. The next one has 4 terms. And often when you have 4 terms, we factor by grouping. Often when you have 4 terms, you factor by grouping. And so if I think of this as x cubed minus x squared minus x plus 1, I could take an x squared out of the first 2, take a negative out of the second. My binomials match. And then it actually continues to factor after that. But it's seeing the 4 terms, but it's more abstract because of the tangent in there. And so for this one, out of the first 2, I can take out a tangent squared. And that leaves me tangent x minus 1. And then right here, I want the binomial to match. I need to take out a negative 1. So a negative out of there gives me a positive tangent x and a minus 1. And so what goes in my first binomial is tangent squared x minus 1. And my second, because these match, is just that tangent x minus 1. So this is tangent squared x minus 1 times tangent x minus 1. But up here where I did it with x squared minus 1 is still a difference of squares. It factors x plus 1, x minus 1. Tangent squared x minus 1 is a difference of squares. It factors tangent x plus 1, tangent x minus 1. And they will probably combine to the quantity tangent x minus 1 squared. And the goal was to factor, so we don't want to expand it from there. I'll just get back what I came from. They want it in factored form. So that's the answer to the factored form. Your assignment today is both partly from the book and part of a worksheet, so I will get that to you.